Hi and hello. This is our control assignment, and we have given question A to be answered, and this is our figure, which is mini packaging system, and transfer function already given for this system. So once we got the transfer function, we can plot the root locus in MATLAB. So this is the root locus that we got. In MATLAB, and this is the calculation for this system that system on the figure above. And so the transfer function is 2s plus 5 over 2s power of 3 plus 2 plus 3s 2s power of 2 plus 40s plus 30, and we got two poles and also one zeros, which is -1 for the pole and -2.5 plus minus J 2.96 for the another pole and -2.5 for the zero. And first of all, we need to find the asymptotics intersect. So the formula is sum of poles minus sum of zeros over number of poles minus number of zeros. So for the this trans function, we got negatives 1.75, and for asymptotic angle of asymptotic, we need to find it. So the formula is 2k plus 1 over the number of branches times 180 degree. So here we got 90 degree and 270 degree for the asymptotic of angle of asymptotes. And for this break-in and breakaway point, there's no break-in and breakaway point for the system. The next procedure is we need to calculate angle of arrival and also angle of departure. For this system, we got angle of departure only. So the formula is 180 plus the sum of zeros minus the sum of poles. So the final answer we got is 26.87 degree for the angle of departure. So the final method is uh, to find the crossing point. So the crossing point, first of all, we need to do the characteristic equation from the transfer function. So we got this as the characteristic equation where 2s power of 3 plus 12s plus 40 plus 2ks plus 30 plus 5k. So we need to do the Roth-Hurwitz table to get the crossing point, where the crossing point we got plus minus j 3.16. So this is the root locus that we have designed on the graph paper using the data that we get from here from the calculations and everything. And secondly, we need to determine the location of dominant poles for the ratio equal to 0.62. So the damping ratio is 0.62, and the dominant pole, from that we need to find the dominant pole where -2.0 plus minus j3. So thirdly, we need to identify the parameter which elaborate the performance of the system that refers to the transient response. So the transient response that we got is zeta omega n equal to 2.4 and omega n equal to 3.87, and the omega d is 8, where we need to find the settling time, the peak time, rise time, and also percentage of overshoot. So the TS, where the settling time is 1.67 second and the peak time is 1.05 second and the rise time is 0.50 second, and finally the overshoot is 8.35 percentage. So identify the parameter which elaborate the performance of the system that refers to the force response. So here we need to find the steady state error. So the steady state error is 0.92, and prove each answer using a MATLAB and Simulink. So before we proceed to the Simulink, we need to find the gain value first. So the gain value we need to find like this, and the answer is 0.54. So once we get into the Simulink, we need to enter the gain 0.54. So this is the block diagram for the transfer function, and we also enter the gain. And once we enter the gain, we can see the graph, which is transition response on the scope of the Simulink. So this is the output of the Simulink, and from the Simulink, from this graph, we can get some values where final value we can get the final value. So from this final value, we can get the TS where 0.0809. So TS equals to 3.414. So we need to use this formula to get the TS. So the TP we can get it from the graph where 9.09 second, and TR is equals to 0.067 second, and everything we need to get it from the graph, and also these calculations and overshoot also. So yes, the overshoot is 0%, but the steady state error is 0.92 from the graph that we got. So through observation, we can say that the system performance is not stable and acceptable because the error is almost 100%. So because we got the steady state error 0.92. So for the system, to improve the system, we need to use the PI controller. So this is the method to find the steady form of the PI. So we will get K bracket S plus 11.1 over S plus 0.001. So this is the form of the PI. Uh, the value of PI. So this value of PI we need to enter at the block here. We just modify the block like this, and once we modified, we can get the transferring response for this improvement after we add the PI controller. So this is the uh, graph for the PI controller, and finally we can get the final value 1 and the steady state error is 0. So that's all for my part, and thank you.
Okay, my name is Ahmadin Ashrafi Ahmadizi. So for my part, I will explain to suggest a proper controller by using bot plot. So to improve the steady state constant, we use the lag compensator controller so that the steady state error can be decreased and increasing the stability of the system. So so this is our calculation for the transfer function that will be used in the system. So we get 37.313. So next, this is the block plot for the system. Above one, this one is for the magnitude slope, uncompensated magnitude slope. The middle one is the lag compensator, and this one is the phase slope, uncompensated phase slope. Okay, this is the calculation for the plot. This is the phase slope and the magnitude slope. So for this plot, this is the compensated magnitude slope and compensated phase slope. So by using Simulink, this is the system that we get using Simulink, and this is the graph. So from the MATLAB, we can know that the final value is 0.9763, and the steady state error 0.0237, which is decreased. This means that steady state error is decreased, so the system is more stable. So this is for the implementing the design controller. So we need to find uh, the capacitance, so we can implement it here. That's all.
Assalamualaikum and a good day. So from the previous question that my friend has presented before, we know that for the system we need to use PI controller to improve the system condition. So we will implement PI controller by using operational amplifier. And for that, first we need to assume our C value, and we assume it is 10 microfarad. Next, from our calculation, we get that our R2 is need to be 2.83 times with 10 with the power of negative 4 ohm, and R1 is negative 5.24 times with 10 with the power of negative 4 ohm. And this is the diagram for schematic diagram for operational amplifier of PI controller. And we need to implement our values into the respective part. For question EI, we need to draw a butt plot of the system with gain equal to 1. And for that, we get this butt plot. The first line, where the damping ratio is equal to 0.645, is the butt plot for when the system gain is equal to 1. Next, from the butt plot, we can see that the gain margin is infinity and the phase margin is also infinity. And the next question, E3, we need to know the gain margin when the damping ratio is equal to 0.405. And from our butt plot, the second line or the second butt plot, damping ratio equal to 0.405. We know that the gain margin is also equal to infinity. For question 4, we need to find the value of gain K that cause this damping ratio. And from our calculation, we got that K is equal to 0.398. Next, we need to prove our answer by using MATLAB or Simulink. And for this question, we have used MATLAB software with RL tool command. So first, for K equal to 1, we got this butt plot with both gain margin and phase margin is infinity. And then next, for K equal to 0.398, or originally in the question is asking for using damping ratio of 0.405, we got that the gain margin is also infinity and phase margin is infinity. So this is the butt plot that we got from the MATLAB software. And lastly, from our observation, we can see that our system performance has stabilized as the phase margin is infinity.